All right, so I did want to also remind everyone, now that I started recording, my recording from last time, I accidentally clicked the button to record to my laptop instead of to the cloud. So for the remote class, I made a little announcement here that has an attachment of the recording to it. So I just uploaded it from my laptop to this announcement right here, and you can get the recording there. For Monday's lecture. In the other class, I just posted it to the bottom of the sort of the list of recordings. So in the online class, rather than the remote class, which are these guys, if you just scroll down to the button, so I said, I hit the wrong button. The recording's attached below this message. So if you scroll all the way down to the bottom, here's that same attachment. That's Monday's lecture. So my apologies there. It's a little different. I just hit the wrong button, but you can download it from that location. Okay, does anyone else have any other questions for me? Okay, in that case, why don't we talk about the midterm? So your midterm was due last night. So I suppose we should go through it, right? Let's see, do I have it here? I don't. Okay, so let me download it. Oh, quizzes. Oh, the graded proof. Thanks, Haruka. Yeah, let me do that as well. So here, why don't we do that first? So I believe the graded proof is about the giving birth to the boys and girls. Isn't that right? Yes. Cool. So the idea there is that a couple is trying to have kids, okay, and they want to have a girl, and they decide to have children until they have a girl, but they'll give up if they have 4 boys in a row. After 4 boys, that's that's time to give up, right? So the question is, what's the expected number of boys and the expected number of girls in their family? Gambler's ruin. Yeah, exactly. So the idea here is you're computing an expected value, which means you're adding up the number of girls in each outcome times the probability of that outcome happening, right? So what are the different outcomes that might happen here? Yeah, that's right, Nathan. So they either just have a girl and then they're done, they have their girl, or they have a boy and then a girl and then they're done, or they have boy, boy, girl, and then they're done, or boy, 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 girl, or boy, 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 in which case they give up, right? So there's 5 different possible outcomes, right? So to find the expected number of girls, you would say, well, in each of the first 4 outcomes, there's 1 girl. In the last outcome, there's 0 girls, right? So you take each of those numbers, 1, 1, 1, 1, 0, multiplied by the probability of each of those outcomes happening, and that would be the total expected number of girls, right? Okay, so let's do an example, right? So the first outcome of just getting a girl on the first try, right? What's the probability of that happening? Yeah, 1/2. We'll assume that having a boy is just as likely to have as having a girl, right? Which isn't exactly true biologically, but it's pretty close enough for our assumptions, right? Okay, so what about the second possibility? They have a boy and then a girl. What's the probability of that happening? Yeah, 1 out of 4, because now you have to have a boy first, which is a 1 in 2 chance of that happening, and a girl second, right? And a girl second, which is a 1 in 2 chance of that happening. So you have that and, so you're multiplying them. 1/2 times 1/2 is a quarter, right? So what do you think, Haruka? Does that give you some insight in how to approach the problem? Yeah, absolutely. Okay. Any other questions on the proofs for this week, or other questions before we jump into the midterm? All right. In that case, let me open it up here. All right, so here's your midterm. Guess I should zoom a little. There we go. Okay. So here's what I've got for sets A and B. Prove that A union B equals A intersect B if and only if A equals B. Okay. So what do you guys think? How would you approach this question? Question one. Four proofs by elements. Okay, that's one approach, definitely. Other ideas? Is that the only way? You can draw a diagram. Okay, so what kind of a diagram did you draw, Kobe? Yeah, Venn diagram. Okay, so how would you show that if the union is the intersection, then that's true if and only if the sets are equal to each other? How would a Venn diagram show that? And A intersect B, if they're equal, the diagrams would come out the same. Oh, I see. Yeah, I missed a comment. Okay, so you drew A union B when they're equal, then you drew A intersect B if they're equal, and they would come out the same. Okay, so Luan, I think I like your idea of combining both, but I'm not sure if we even need a diagram to do it. I think one direction of the arrow, the reverse direction, if A equals B, then the union equals the intersection. I don't even think you really need an argument by elements to do that. I think you can just do a substitution, right? Because if A equals B, then what's A union B equal to? Good, right? If A equals B, then A union B equals A union A. Or what is A intersect B going to be? Yeah, A intersect A, right? Because you can just substitute, right? Because they're equal to each other. And since A union A equals A and A intersect A equals A, then they're equal to each other, right? So I think you can do just a simple substitution to prove the sort of left pointing arrow, the reverse pointing arrow. But the forward arrow, if the union equals the intersection, then the two sets are equal. I think that would require a proof by elements, or possibly a Venn diagram. But I think it's going to be tough to sort of argue with a Venn diagram why it is that if the union equals the intersection, then the two sets are equal to each other. Did anyone try to do a Venn diagram for that direction of the arrow? And if so, what was your argumentation like? Okay, I guess not. Or if you did, feel free to jump in. What would a proof by elements look like here? Maybe I should switch over to a video. for me. There it goes. Okay, so what we want to show is that A union B equals A intersect B implies A equals B.
So the way I did the proof by elements, you have to do two proofs for this one because you have to show that A is contained in B and B is contained in A.
Mhm.
So you pick an arbitrary element of A and show that it's an element of B, and then you do the same thing to show that they're equal. And then you do the other side of the arrow where you take A equals B as your premise and then show that A union B equals A intersect B by doing two contains proofs.
Sure. Okay. So in that case, so that for that second case, that's one I was talking about before, going the other direction. If you have A equals B implies A union B equals A intersect B, I think you can do that just from a substitution, right? Or as Lucas says here, algebraic, right? Because if A equals B, what does that mean? Well, that means you can substitute A union A equals A intersect A, which implies A equals A, and you're done. Right? So that's going the right-hand direction. Going the left-hand direction, we could do a proof by elements to show that A is contained in B and B is contained in A, which means that they're equal. Or Lucas says you can also do an algebraic proof. Okay, so how would an algebraic proof work, Lucas? How do I derive A equals B from this guy? Maybe Lucas, while you're thinking, why don't I do the proof by elements? Or I'll just do one of them, right? Oh, no, you got it already. Okay. A is a subset of A union B, which is a subset of A intersect B, which is a subset of B. Okay, so you said A is inside of A union B. And we know that A union B equals A intersect B by our premise, which is contained in B. Right? So this proves that A is contained in B. Right? Or going the other way, you could say B is contained in A union B, which of course is equal to A intersect B, which is contained in A, which of course proves that B is contained in A, so therefore A equals B. Okay, so that's a nice algebraic way of doing it. Or you could do a proof by elements. So let me do a proof by elements here just to give you an example. So we would say, let X be an element of A. Well, we know that if X is an element of A, then what? Well, then X is an element of A intersect B, which means X is an element of A union B, because the intersection is always contained in the union, right? Oh, or, is that the right way to go? Because we want to end up with X's inside of B, right? So I think I made a wrong turn here. Where should I have gone for this proof by elements? Yeah, this works because I have equals in the premise. But now that I have X inside of A union B, or yeah, A union B, I want to end up with X being inside of B, but I don't really see how to get there from here. So where do I go next? Maybe if X is in A intersect B, then X is in B. So all I need here is just a B, and then I don't need any of this other stuff. Is that right? Maybe I went the wrong direction, possibly. So if X is in A, I don't actually know this at all. If X is in A, what do I know about X in terms of A and B? Yeah, that means it's an A union B, right? Which means then X is in A intersect B, since A intersect B equals A union B. And finally, X is in B, right? If X is in A, then of course it's got to be in the union. If it's in the union, then it's in the intersection because they're equal by our premise. And if X is in the intersection of two sets, well, then of course it's in both sets, so it must be inside of B. So there's an example of one of the two directions of the proof by elements. What do you guys think? Okay, so David, you're saying if you use a Venn diagram, say you throw a dart at it, and it needs to be 100% chance that the dart hits A intersect B. Well, I'm not quite sure. You're involving throwing a dart here, which I think is a little bit like this variable X being in A. We're saying think of X being the location where you throw the dart, and you don't know where it is, right? X is a variable, just like where the dart hits is going to be a variable, right? So I think that, I think that your thinking is similar to a proof by elements, right? So, okay, that's a little bit cleaner now. Let's sort of see how it goes. So, you can sort of discuss the idea of what it means for the union and the intersection to be the same. And you could certainly use a dart throw to discuss that. But I'm not sure if that constitutes a proof, David. Maybe you could hop on the mic and give a little more detail.
I guess just if you have you'd think of A as one dartboard and B is the other dartboard. And if you have the union and you randomly throw a dart, then you have uh, you need the probability of A union B. The area of A union B would need to equal the area of A intersection B.
Mm-hmm.
Um,
That's what this is saying, this premise, right?
yeah.
Okay.
And in that case, then A and B would have to perfectly overlap.
Why?
Because if there's portions of A or B sticking out from each other, then you'd have a % chance of getting A but not B.
Okay, so in that case, it seems like you're doing a proof by contrapositive, right? You're saying if A is not equal to B, then these things are not equal to each other, right? That's the sticking out part, right?
Yeah.
Yeah, and I think you could certainly do a proof by contrapositive here, which would be saying that if A does not equal B, then A union B is not equal to A intersect B. Sure, and you could prove that for going the other direction, right? And so if A does not equal B, right, then how would you prove this contrapositive? Any ideas? Okay, so let me help, right? So if A is not equal to B, that means that one of two things is true, or both, okay? Which is that there's something in A that's not in B, or there's something in B that's not in A, or both, okay? It doesn't really matter which one we pick, it's going to turn out the same either way. So without loss of generality, let X be an element of A and, excuse me, and X is not an element of B. You could go the other way. You could say X is an element of B, but not an element of A. But it doesn't matter which way you go. It's sort of symmetric in that sense, right? So if X is in A, but not in B, what does that mean about the union and the intersection? Well, if X is in A, but not in B, is it going to be in the union? So you have an element that's in A and not in B. Is that inside the union of A and B? Yes, right? Because it's in one or the other, and it's in one of them, right? For the union is like or, right? So we're saying something's in A or B. And since this is in A, well, then it's in one or the other. So X is an element of A union B. But this guy, right, A intersect B, that's and, right? Is X in A and B? No, right? It's only in A. It's not in B, right? So X is not an element of A intersect B. And since we have an element that's in one but not in the other, then in conclusion, A union B is not equal to A intersect B. There's a little proof. What do you guys think? Does that make sense? Makes sense. Okay. Shall we move on? Do we have other questions on this one, or are you guys good? Good. Okay. So let's try another one. Let's try number 2. Number 2 says you want to prove that Z, the size of the integers, equals the size of the naturals by showing that there's a bijective function f from Z to n. Okay. So it says you have to give an explicit bijective function. Okay, so we'll give a function and we'll show that it's bijective. So what kind of a function did you guys come up with? Okay, fz equals 2z if z is positive or 0. Okay, so f of z equals 2z when z is greater than or equal to 0. And it's equal to 2z minus 1. Oh, sorry, negative 2z minus 1 when z is less than 0. 0 is in the naturals. If you start the naturals at 1, that's fine. I wouldn't take points off for that. You can really do it either way. This function you would have to change a little bit if you're not including 0 in the naturals. So we will be including 0 in the naturals here just because we're doing this one. It doesn't really matter either way. It's still the same idea, right? Yeah, explicitly map 0 to 1. That's fine. Yeah, no big deal. Okay, so what's happening here is the positive numbers go to 0, 2, 4, 6, 8, 10, etc. Right? So you would have, if we made a little number line here, we have, 0, 1, 2, 3, 4, -1, -2, -3, -4. Okay, so 0 is going to go to 0, 1 is going to go to 2, 4, 6, 8. -1 is going to go to negative 2z minus 1. So it would be -2 times -1 is 2, minus 1 is 1. 4 minus 1 is 3. 6 minus 1 is 5. So 1, 3, 5, 7, etc. And so I think we've hit, all of the natural numbers in our mapping, in our function here. How do we know that this is bijective? Yeah, you can show it's 1 to 1 and onto. And I think you can get away with just doing one of those two things. There's kind of a shortcut on one of them. Does anyone see what the shortcut is? You didn't see the shortcut, okay. Well, we can forget about the shortcut. We can prove that they're 1 to 1 and onto. What does that mean? Right, let's start with 1 to 1. What does it mean that our function is going to be 1 to 1? Okay, for all z's, if f of z1 equals f of z2, then z1 equals z2. Okay, that's the 1 to 1 idea. Did you have to prove the function was bijective? Well, I think there should be some discussion at least. I mean, you're supposed to give a bijective function. So, there should probably be some discussion as to whether or not your function is actually bijective or not, right? So I guess, Sean, at least somewhat. Yeah, I think a diagram would suffice. Sure, why not? Right. So Natasha, what kind of diagram did you provide to give that argument? similar to the one we did in class, z on the left and n on the right. Oh, okay, so you drew an arrow diagram. That's what you're saying? Okay, so you drew an arrow diagram, and it seemed clear from that diagram that your function is bijective. That everything on the right-hand side is covered. That would be onto, right? So 0, 1, 2, 3, 4, 5. Everything has an arrow going to it, right? And then you showed that it's 1 to 1, which is that two things on the left can't map to the same thing on the right, right? That's 1 to 1. And I think that could be pretty clear from the diagram, right? That you can never, you're never going to get the same natural number popping out with this function. Okay, you drew a little diagram too. Yeah, that's fine. As long as there's some, there should be some kind of discussion as to why this thing is bijective. I mean, if you just gave the function and I might take a couple points off for that. If you just gave a function and didn't talk at all about why it's bijective, that's not really like getting you're not getting the whole answer there, right? But I think an arrow diagram will be fine. You could do a more explicit proof, like Lucas was discussing. I think that's fine. Sorry, David, you had a question here in the chat. If you said negative numbers and positive numbers are mapped to positive numbers of the opposite parity from 0 to infinity. Well, I don't think that works, right? Because the opposite parity of what? The opposite parity of the parity of the integer? Because sometimes, an odd integer goes to an odd, an odd integer here. Odd integer goes to an odd natural, but sometimes an even integer goes to an odd natural. So David, I'm not sure that necessarily works. Because here we have an odd going to an odd, but here we have an even going to an odd, right? Okay, so the sign corresponds to the parity. Okay, yeah, that makes sense, which is essentially what we were saying here, right? But as I said, I did need you to give an explicit function. So if you said literally what you just said in the chat, positive goes to even, negative goes to odd, then I would give you, most of the credit, but I really did want like a little formula like this for that explicit function, right? Does that make sense? Okay. So we could, that was your explanation of why it's bijective. Yeah, okay, sure, yeah, that makes sense, right? Because the positive goes to the evens, the negative go to the odds. So everything is covered and nothing gets, two things mapping to the same one, right? Because different positive numbers map to different even numbers. So if they're both positive, they can't map to the same thing. If they're both negative, they can't map to the same thing, because again, this is a bijective function here. And of course, if they're, if one's negative and one's positive, of course they can't map to the same thing, because one's going to go to an even and one's going to go to the odd, which can't be the same number, right? Yeah, so that's a fine argument, David. I think that's great. Yeah. Okay. So I think that's fine for our discussion there. How about the last little part? How does that show that 2 times infinity is still equal to infinity? Someone want to discuss that idea? You can count function and the inverse function the same way. Not quite sure what you mean by that, David. Okay, Lucas said you could make a function assigning 2 integers to every natural. Kinda. I mean, I was looking for something a little bit simpler than that. Okay, so you have 2 times the size of the naturals is the integers, because you have twice as many integers as naturals. You have all the naturals, then you have the negative versions of all of them, right? So you have double the amount of naturals, that's the integers, right? But they're actually equal to each other, right? So 2 times the naturals equals the naturals, and 2 times infinity equals infinity. Yeah, Lucas, I think that's a really nice train of logic there, right? So long as you have a little explanation as to the very first step, why is it that 2 times the naturals equals the integers, right? And the answer is, well, because there's a positive and a negative natural, of the same natural. There's a positive 3 and a negative 3 inside the integers, right? So there's twice as many integers as there are naturals, right? Any questions there? Does that make sense? Okay, so what about the third question, right? Explain why Stirling numbers can be used to count surjective functions and find the number of distinct surjective functions. Surjective means onto, right? The number of distinct onto functions from the set A, B, C, D, E to the set 1, 2, 3. Okay, so first of all, here, let me pop over to the share screen for a moment here. Let's talk about, I included this, this guy here, which is this information from the book, right? So you can find Stirling numbers, the number of ways a set of size n can be partitioned into R subsets, right? So in order to find the answer of, how many ways can you have a set of 5, A, B, C, D, E, mapping onto a set of 1, 2, 3. Oh, I guess I should be sharing screen, or sharing video, sorry. There we go. Okay, so I've got sort of this situation here is what I'm looking at, right? And so someone maybe just discuss this for a moment with me here. So why do Stirling numbers have anything to do with onto functions? Someone describe that to me. Okay, so here's the question one more time. Stirling numbers show you the number of ways a set can be partitioned into subsets. What am I partitioning here in order to find onto functions, and why am I partitioning something? How does that work?
So you're essentially asking, how can you divide up the 5 elements in A, B, C, D, E into 3 groups of elements? Because
Okay.
for an onto function, two of the elements in the domain can point to the same element in the codomain. That's fine.
Yep.
3 of them can point to the same element in the codomain, but everything in the codomain needs to be pointed to, and everything in the domain needs to point to something.
Sure. So we're partitioning the domain into 3 subsets, right?
Right, yeah.
So maybe, I'll partition it here and here, right? So I have A in one partition, B, C, and D in another, and E in the last partition, right? And once I do a partition, then what does that have to do with my arrows? Like, where are the arrows going to go in this diagram and why? Each subset points to one of the three elements in the codomain. Perfect. And we get to pick which. So maybe E, maps over to 1, A maps to 2, and then B, C, and D, all of them map to 3. Right? So that's B and C and D. All map to 3. Right? Yeah, every element in the subset points to one of those codomain elements, right? So really what I'm looking for here, what I'm trying to find with my Stirling numbers is I'm trying to find S of 5, 3, right? Because I'm trying to find, the number of ways that I can take a set of 5 elements and partition it into 3 parts, which I've done here. Part A, part B, C, D, and then part E is the third part, right? And then once I have that partition, then I map each one of those subsets to one of the elements in my codomain, right? Okay, so I'm looking for S of 5, 3, right? And I can certainly figure out how to do that. Where's my little formula here? Where is it? There it is. Okay. This equals S sub n minus 1 r minus 1 plus r times S sub n minus 1 r. And it is 25. That's right. So this is going to be equal to S of 4, 2 plus r is equal to 3 here. So 3 times S sub n minus 1 r. So that would be 4, 3. So S of 4, 3, right? But you don't multiply by 3, you multiply by 3 factorial at the end, it turns out. Right? But before we get there, let's find this guy, right? So this is going to equal what? Well, it actually has a bunch of examples on here, right? There's all my examples. Oh, it died. Wait, where's my, I thought it gave examples of S4. Oh, wait, here it is. Right. So here we've got S44 equals 1, S42 equals 7. Okay, so this guy's a 7 plus 3 times S43, whereas S43 right here equals 6, right? And 7 plus 3 times 6 is 25, right? And if you read that, it actually has those values for S sitting right in the text over here. Yeah. So, okay, so that's S of 5, 3. And that's how many different ways you can partition your domain. Once the domain is partitioned, then you have to decide which part maps to which codomain element, right? And how many ways are there to do that? Well, I have 3 choices for the first part, 2 choices remaining for the second part, and 1 choice for the third part. So the total number of onto functions would be 25 times 3 factorial, which of course 25 times 6 is 150. And that's your answer. Yeah, if you forgot the factorial, I'll take a couple points off. But if you got the, if you described and correctly got the Stirling number part, that's going to be, quite a bit of credit for doing that part at least. What do you guys think? Questions? Okay, so then here's number 4. Given a set A of size n, what's the probability that a randomly chosen relation is reflexive and symmetric? Okay, so I'm gonna pop back out to a full view here. Let me stop sharing. And okay, so I've got the size of set A equals n, right? And R goes from A to A. Oops, R goes from, goes from A to A, right? And I need R, I want the probability R is reflexive and symmetric. Okay, so I think a good place to start here is to think about what could be in this relation in the first place. And so if we have a set A and the relation is going from A to A, what could you have in your relation? Should we do an example? People have a good abstract idea of what's happening here? Could just have them all be reflexive. So I'm not quite sure what you mean by that, but I don't think that quite relates to what I was asking. So let me try asking my question one more time. In a relation is just a set, okay? It's a set of pairs, right? So what kinds of things are going to be in my relation here? Let's do an example. Let's say A equals the set 1, 2, 3, 4. Right? Okay, we're gonna have a set of ordered pairs where both parts are from A. So as an example for a relation, I could have the relation be the set, of the pairs 1, 2, 1, 1, 1, 2, 3, 1, and 4, 3. That would be an example of a relation, right? Now here's my question to you guys. Where are these pairs coming from? Like, what are all the possible pairs? Or let me ask it a little better. What's a really pretty and elegant way of representing all the possible pairs that may or may not end up in my relation? Yeah, there are n squared possible pairs, right? So I think a nice way of thinking about that is if you have a little table. Okay, so here's a table with the inputs on one side from A and the outputs on the other side. So in here would be the pair, 1, 1. Here would be 1, 2. Here would be 1, 3. And here would be 1, 4. Right? On the next row, you could have the pairs, 2, 1, 2, 2, 2, 3, 2, 4, and so on. Right? I guess I can write them all out. Maybe it'll be easier to understand this way. Okay, so those are all the pairs that may or may not be in my relation. Notice I said may or may not, meaning that each one of these guys is going to contribute a factor of 2 to my total number of possibilities, right? So the total number of possibilities is 2 to the n squared total possible relations. So when I do my probability, this is what I'm going to be dividing by at the end. That's my grand total. right? Since each one of these can be either in or out, that means that, you know, there's 2 to that number total, and this number is, of course, is just n squared, right? Any questions so far? Does that make sense? You thought about it, that the first part of the ordered pair could come from any element of the power set of A. The second could come from any element of the power set. So the number is size of the power set. No, unfortunately, that's not quite right. That has the squared in a different place, right? So for example, if I had, let me come up here, if I had 2 to the 5 squared, that would be 2 to the 25th, right? But the way that you were talking about it, you were saying the size of the power set times the size of the power set, which would be 2 to the 5th quantity squared, like this, which would be 32 squared, which is not the same number, right? So Sean, unfortunately, I don't think that way is correct. You sort of got the parentheses wrong on this formula. They should have been there, right? Yeah, it was different. Okay. Other questions on sort of this kind of layout here? Okay, so then let's talk about the meaning of reflexive and symmetric in terms of the possible elements we could include, right? If my relation has to be reflexive, the number of choices of what I'm able to include or not include in this table are limited. What gets limited out if I'm requiring that my relation be reflexive? What am I not allowed to choose anymore? N pairs must be in the relation. Which ones? The repeats, right? I would say down the diagonal. 1, 1 has got to be in there in order for it to be reflexive. So does 2, 2, and 3, 3, and 4, 4. Those all have to be in the relation, so I don't get to pick them anymore, right? Is everybody happy with that? So my number of choices has now decreased, as you said, by n pairs, right? But I also need my relation to be symmetric. So what does that mean in terms of my little table here? Ideas? So let's say I want, okay, if x are y, then y are x. So if 2, 1 is in there, then 1, 2 has to be, right? So if I say 2, 1 is in there, then 1, 2, that can't be chosen, right? What if I say 3, 1 is not in there? What does that mean about 1, 3? So if 3, 1 is not in my relation, that also means that this one's not in there, okay? What if I say 3, 2, this one is in there? Well, of course, then 2, 3 has to be in there, right? And so on. Maybe all of the 4s are in there. Well, let's do, you know, this one and this one are in there. That means this one and this one have to be. This one's not means that this one's not. So what did I actually get to pick? Well, I only got to pick one of these 2 triangles worth of stuff. I only got to pick this, right? The diagonal has to be in there, and the upper triangle up here is just going to be a reflection of the lower triangle. So I don't get to pick this or this, right? These are all out. I don't get to pick them. The only thing I get to pick is 1 triangle's worth, right? Well, okay, So how many is that in terms of n? N squared minus n over 2. Okay, so in this case, n squared minus n over 2. So that would be what? That would be 4 squared minus 4. So 16 minus 4 is 12 over 2 is 6. Good, right? And that's just Gauss's formula that we learned about last term, right? Excuse me. So what do I actually get to pick? Well, I actually get to pick this many pairs. So my total number of options is 2 to this number, right? So what I'm actually, my actual probability is going to be 2 to this number. So 2 to the n squared minus n over 2 divided by 2 to the n squared. That's my probability. If you got this, full credit, right? But you can simplify this a bit. Let's see if we can do that, right? So what would simplification of this look like? Two to the what? If you divide exponents, right, then what, and you want to sort of simplify it, what arithmetic operation does that turn into if you're dividing exponents? What do you do with them? Assuming that you have the same base, of course, which we do. Yeah, you subtract them, right? So this would be 2 to the n squared minus n over 2 minus n squared. 2 to that whole power. And of course, we could simplify this guy a bit. So what will we have here in our simplification? Two to the what? Okay, negative n squared minus n over 2. Negative n squared minus n over 2. And of course, if we have negatives in the, in an exponent, that means that we pop the whole thing down into the denominator. So we could say this whole thing is 1 over 2 to the n squared plus n over 2. And there's a little simplified answer. What do you guys think? Questions? Okay, cool. So let's go move on to the last one. Here we go. All right, so the last one here. Using a combinatorial argument, explain why choosing R elements from sets of size m and n gives the following equation. So let me write the equation down here. M plus n, choose R, equals the sum from I equals 0 to R of m choose I times n choose R minus I. And I wanted you to give a combinatorial argument explaining why this is true. So what do you guys think? Someone want to hop on the mic and give me a couple sentences?
All right, so the first term, obviously, you're choosing R elements from a total of m plus n elements, right? So that's the left-hand side of that equation.
Yep.
And on the right-hand side, ignore the summation for now. Just look at the two terms. You've got two combinations. One is you're going to choose I elements from the first set of M elements. And now you've got the R minus I elements left to choose, and you're going to choose those from N. Since you're choosing from N, M, and from N, you use the multiplication rule.
Okay, so what you're saying is you're choosing at the beginning of this summation, for example, the very first term, you'd be choosing 0 elements from M and R elements from N, right?
Yep.
So nothing from N, nothing from M, all R of them from N. Right?
And then the next term, you can choose them that way, or you can choose them where you choose 1 from M and 4 from, or I think I might have written an example with 5 in it, but the
sure.
1 from M and R minus 1 from N. And since that's an or, you use addition, which is why there's this summation, because then you're going to go all the way up to the point where you're choosing all R from M and 0 from N.
All the way up to the point where we choose all R of them from M and none of them from N. Beautiful. Yeah, it's perfect. Right? Is everybody happy with that combinatorial argument? All that it's doing is saying you're going to pick some of them from M and some of them from N, right? And so that's the and, which is the multiply there. I of them from M and R minus I, the rest of them from N, for every different possible sort of distribution, which are all your different I's. Since you can do, 1 from M or 5 from M or 3 from M or whatever, all those ors are all added together, which gives you that summation. Yeah, that's great. Any questions there? Does that make sense? Okay, so the second part, by letting all three of these things equal each other, show that the sum from I equals 0 to N of N choose I quantity squared equals, 2N choose N. Right? So, okay, so letting R equals M equals N, well, if these are all equal to each other, right, then M equals N. So starting on the left side, this thing is equal to N, this thing is equal to N, this already is an N. So I have N plus N choose N. So on the left, I have N plus N choose N equals 2N choose N. That's on the left, right? And that's going to be equal to the sum from I equals 0 to N now, because there's just all going to be N's, right? Of N choose I times N choose N minus I. Now what? What I'm shooting for is the sum of N choose I squared. So really what I want this right-hand thing, yeah, that's going to transform into N choose I, which is going to give us that N choose I quantity squared since I'm multiplying in here, right? And why is that, David? Why is it that N choose I equals N choose N minus I? There's a few different ways you could say why that is. There's kind of an easy way and a hard way. From the book, okay. You could cite the book. You can say, okay, this is a theme. There's 3 ways. The easiest way is to say, here's a page number, right? Here's a reference to the book. The book says so. Done. Sure, that's fine. I'll accept that, right? So what are some other ways to do it? Maybe you didn't find it in the book. You didn't know it was there. Yep, you could use the formula for choose notation, right? You could say, you know, n factorial divided by n minus n plus I factorial times n minus I factorial, right, is equal to n factorial times I factorial times n minus I factorial, right? So this one comes from this guy. I guess I should have done them in the same order, sorry. This one is coming from this guy by the formula. This one is coming from this guy from the formula. And obviously these 2 things are equal because the n's cancel right there. Okay, so that's a pretty easy way. Another way of thinking about it is thinking about Pascal's triangle, right? If you're in row n, column I, right? So that means that you're in row n and you're taking I steps in the triangle from left to right, right? Starting from the left side, you take I steps inward to find your answer. This one, n minus I, means you're starting at the right-hand side, taking I steps toward the left to find your answer, right? And since the triangle is symmetric, right, it's horizontally symmetric because you can go from this to this side and back, right? Then these 2 things have got to be equal because of the symmetry of Pascal's triangle. That's another way you could argue it, right? What do you guys think? Does that make you happy? Questions? Okay. Well, let me ask you this. I adapted this test because last year it was a take-home exam, and I made it a bit easier so it could be a timed exam. What did you guys think about the difficulty? Did you think it was pretty close to in line with the exams from last term? Those of you that had me before, those of you that haven't had me before, did you think it was a good test? Did you do well? Did you do terribly? What were people's impression here? Because I haven't started grading; they were due last night. So, what were y'all's impression of the test? Okay, you had to rush a bit at the end. Okay, that's fair. The new problem type introduced on the test. What do you mean by that, Amber? I'm not sure what you mean by the new problem type. Oh, the Sterling numbers, right. So yeah, so that one I tried to make a bit easier by including the actual text from the book that it referenced, rather than just leaving it to you to figure it out. And I haven't done a question like that before, where I guess it was sort of a reading question, right? So I had you guys, read about this question for the first time, probably during the test, unless you happen to, really get into Sterling numbers when you were studying, which probably you didn't, right? Yeah, so that was a new kind of question where I sort of gave you all the reading during the test, but it was new material rather than not giving you any of the reading and having it be old material. So I sort of thought of number 3 as a little bit like a book report, right? Like I gave you all this new information and said, okay, analyze this and and use it. Yeah, so that was a new kind of question. So I feel you on that. Okay, people are saying it's harder than the final. Okay. So what did people think about question 3 in general? Because that was the first time I've ever given a question like that. Did people, it seems like, let's see, who was that? Amber? Yeah, Amber. So Amber didn't like that, which is fine. What were other people's impression? Oh, and Raphael says you missed it as well. Oh, you missed the reading? Oh, did you just not see the attached file below, Raphael? Was that the problem? Well, not file, but the attached, the attached PDF of the, pictures of the reading there. Yeah, I see. The parts you left for the end took you longer. And Tamara, you did like number 3. Not sure if you were able to word it. Okay. So some people liked it, some people didn't. Okay, that's fine. You forgot to multiply by that 3 factorial. Yeah, that's tough, but that's okay. I'll take off 5 points at most for that out of 25. So you won't get punished too badly for that. But you like the idea of having a short topic. Yeah, it's a little bit more like like a reading comprehension question or something like this, right? So yeah, I was curious what you thought about that. Sounds like some people liked it, some people didn't, which that makes sense to me. Okay. Any other impressions you want to let me know? Anyone else have any comments about the exam? Well, let me ask you this. What do people think about the final? Would you like to have another timed exam like this one? Or would you want one that's a little bit harder that you have like 3 days to work on it? Anyone have any strong opinions about that? Another timed one? Anyone else? Time. Okay. Anyone disagree? Anyone prefer to switch it over to a take-home exam for the final? Okay, David, we got 1 for a take-home. Anyone else rather have a take-home exam for the final? Still prefer the timed. Okay. Well, let me say this. If you really, really want to have a take-home exam for the final, email me. And if I get a bunch of emails, then we'll have a vote or whatever. But otherwise, I'll just assume that you want another timed exam for the final as well. Yeah. Okay with anything. Okay. Easy squeezy. All right. Well, in that case, we're about halfway through. So why don't we stop here? We'll take a break, come back in 10, and we'll jump back into some more discussion about our drunkard's walk from last time. Okay. So see you soon. Back in 10. All right. So I wanted to jump back into our discussion of the random walk that we were talking about last time. And let's start with just a quick little recap, right? So we were talking about a walk in which you're equally likely to walk left or right. So this is a one-dimensional random walk. Okay. So let's do a couple of examples here, right? If we take 0 steps, we do n and let's do steps. Well, let's see, what do I want to call this one? Well, let me call this EV. And then I'll call this the steps. Okay, so if we take, steps is not really a word. Let me call this total. I'll call this total. Okay. I'll explain what we're doing with this column in a second. But we started this little table last time, right? Where if we take n steps, the expected value is going to be, of course, 0, because we're still sitting at 0. If we take 1 step, then the expected value of our distance from the origin, EV is our distance from the origin, remember? Well, we might make a step left, or we might make a step right. Either way, what's the expected value of our distance from the origin? One, right? So if I go left, I'm 1 away from the origin. If I go right, I'm 1 away from the origin. Either way, I'm 1 away from the origin. What if I take 2 steps? Well, if I take 2 steps, then something interesting starts to happen, right? Because then I could take a left, a left right, a right left, or a right right. Those are my 4 combinations of steps. Of course, there's 1 of these, 2 of these, and 1 of these, right? That's my total, right? My total number of combinations that I could get, right? Times the distance away I'm going to be. So if I go left, left, right, that means I'm 2 away from the origin. This one is I'm 0 away from the origin because I go left, right, or I go right, left. Either way, I'm back where I started. And then right, right, again, means I'm 2 away from the origin, right? And so if I add all of these up, that would be 2 plus 0 plus 2 is 4, divided by the total, which is 4 of them. Well, 4 over 4 gives me an expected value of 1, right? For my totals here, my total, I'm just not dividing by 2 to the n at the end. So what I want to sort of throw in here is, let me throw a 4 in here, right? Because this total is 4, and then I'm dividing by 2 to the 2 equals 1 for the expected value. So for the total, I'm just sort of shooting for this number. Okay? It's going to help when we try to figure out a formula for this in a minute here. Okay, what if I do 3 steps, right? Well, how many possible combinations am I going to have with 3 steps? More than 5. 8, right? So I can go left, left, left. You can go left, left, right, left, right, left, or right, left, left. There's those 3. I can do 2 rightward steps, which will be left, right, 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 left, right, or left, right, right, left. Or I can go all rights. Okay. Now in this situation, there's 1 of these, there's 3 of these, there's 3 of these, and there's 1 of these. Now, what distance away am I going to be for each of these guys? So if I go left, 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 what's my distance from the origin? Three. What if I go 2 lefts and a right? Then what's my distance from the origin? 1. Here, same thing, right? Because here I'd go 2 rights and a left, so I'll be 1 away from the origin. And triple right, how far am I? Three, right? So my total here is 3 plus 3 plus 3 plus 3. So my total is going to be 12. And then I'm dividing by 2 cubed. So my grand total is 3/2. Okay, let's do another one, right? So maybe you could help me set up this next one. So where are these first numbers coming from? The left-hand side of the product. Where am I generating these numbers? Like 1, 3, 3, 1. Where do those come from? The combinations of steps to get there. They come from Pascal's triangle, right? Okay, so on the 4 number of steps, what are the sort of the list of entries in Pascal's triangle that I'm going to use to come out with my total? Yeah, 1, 4, 6, 4, 1. 1 times something plus 4 times something plus 6 times something plus 4 times something plus 1 times something. And what are the somethings? Well, that's my distance from the origin that I'm going to be. So if I take 4 leftward steps, right, L, 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 what's my distance going to be? So what's this first blank going to be right here? Four. There are 4 ways to go 3 lefts and a right. So 3 lefts and a right. What's my distance from the origin going to be? 2. This next one? 2 lefts, 2 rights, 0. This one? 2. And the last one, all rights, is a 4. Beautiful. So let's find my total. 4 plus 8 plus 0 plus 8 plus 4. Well, 4 plus 8 is 12. 12 times 2 is 24. Right? So my total is 24. Now I'm dividing by 2 to the 4th total possibilities, because there's 16 total possibilities. And 24 over 16 gives me another 3/2. Maybe we should fill in the ones that we missed. The total up here would be 1 left, right? And 1 right. So it'd be 1 times 1 plus 1 times 1. That gives me a 2 right here, right? And then for the zeros, well, that's just a 0 total, right? Okay. So let's try another one. What's the next row in Pascal's triangle that I'm shooting for? For n equals 5 right here. Okay, 1, 5, 10, 10, 5, 1. 1, 5, 10, 10, 5, 1. Okay. And now what are my distances going to be? Well, if I go 5 to the left, right, then where am I going to be at? Five away. Next one, 5 to the left, 1 to the right. Sorry, 4 to the left, 1 to the right, pardon me. 3 away. This one, 1, right? 3 to the left, 2 to the right. Or 2 to the left, 3 to the right, also gives me 1 away. This one is 4 to the left, 4 to the right, 1 to the left, which gives me how much? 3. And lastly, that one's 5 away. So these are my totals looking like here. So I've got, and it's just doubled on the other side, right? You can see there's a sort of symmetry here, right? Where this side and this side are equal to each other, right? So here I've got 5, 15 is 20, plus 10 makes 30, 30 times 2 is 60. What am I dividing by here to get my, my probability right for my expected value? Yeah, 32, right? 2 to the 5th. And 60 divided by 32 gives me 15/8. What do you think my answer should be here for n equals 6 if our pattern continues? Also 15/8. It looks like we just repeat each number 2 times for the odd and then the even, odd and even, odd and even. So we would expect this to be 15/8 if we do it correctly. Let's do one more and see if that's true. Right? So in Pascal's triangle, what's my row going to be? So the 6th row of Pascal's triangle? Excellent. 1, 6, 15, 20, 15, 6, 1. Okay. And what are the distances that I'm going to fill in? What's the pattern going to be there? Maybe I should do a little bit of highlighting while you respond here. Let's do the Pascal's triangle numbers in yellow and the distances in pink. Yeah, 6420, right? 6420, and then going back the other way, 246 on the other side, right? Okay, so again, here's Pascal's triangle numbers. Pascal's triangle numbers. And then let me go through, do the distances. Let's do the distances in pink. 4, then 2, then 0, 2, 4, 5, 3, 1, 1, 3, 5, 6, 4, 2, 0, 2, 4, 6, right? What am I looking at for my total here? Got 30 plus 24 plus 6. 24 and 6 is 30. Another 30 made 60. And then 60 doubled is 120. And of course, since this number doubled and the amount that I'm dividing by doubles, I go from 2 to the 5th to 2 to the 6th, my expected value should stay the same, right? Everybody happy so far? Any questions? Okay. So what I'd like to do then is I'd like to make a formula that will generate one of these guys, right? And then solve the formula, right? And figure out, you know, a nice closed form solution to find, first of all, my total. And then if I just divide that by 2 to the n, I'll come out with my expected value, right? So maybe let's just come out with a formula at first, right? So my formula for one of these guys, what's this going to look like, do you think? How can we divide that up? Well, so I'm adding a bunch of stuff. So what should the first part of my formula be? Let's maybe base it on this one where n equals 5. I can base my formula on this one. I think will be nice, right? So I'm adding a bunch of things. What am I adding and why? Okay, yeah. So n choose 1 times n plus n choose 2 times n minus 2. You're really close. This would actually be n choose 0 to start. N choose 0, n choose 1, n choose 2, right? And I do want to keep subtracting, but only up to a point, right? Because you said for the distances, we have n, n minus 2, n minus 4, which is right. But then this one is not going to be n minus 6. It kind of goes back the other direction afterward, right? And a really nice thing about this is that not only do the distances count down 5, 3, 1, and then count back up 1, 3, 5, but the numbers in Pascal's triangle are doing the exact same thing, right? We go 1, 5, 10, and then 10, 5, 1. So these two sides are identical to each other. This side and this side are exactly the same. So I can multiply by 2 for my formula, right? I'll have 2 times some kind of summation, right? Now, how far am I going to be summing? Now, remember, n equals 5. So I want to sum from I equals 0 up to what? Depends on if it's even or odd, but let's just stick with this case where n is odd, right? So what are we going to do in that case? Okay, it would be till n plus 1 over 2. Well, not quite, because remember, this is term 0, this is term 1, and this is term 2. So I actually only want to go up to 2 rather than 3. Yeah, so it'll be n minus 1 over 2. You got to start counting at 0 rather than at 1. It's one of those, it's like an array, right? So it'll be n minus 1 over 2 instead of n plus 1 over 2. Okay, cool. And then inside, as Sean said earlier, we're going to have n choose something times n minus something. Okay, n choose I times n minus what? N minus 2i, right? Because my first one will be 5 choose 0 is 1 times n minus 2 times 0. 5 minus 0 is 5. Okay, the next one, 5 choose 1 is 5. This part, 5 minus 2 times 1 is 3. Here's my last one, 5 choose 2 is 10 times 5 minus 2 times 2 is 1, right? So here's our little formula for our total. If I wanted my expected value, all I need to do is take my total and divide by 2 to the n, and I'll come out with my expected value. So I'll just leave that part till the end for a minute. I won't complicate this with extra factors. Okay. So now what I'd like to do is try to solve this formula, and this is where we left off last time. So this was just a little review to get people back on the same page. Let me pause here. Who has questions about this? Does the derivation of the summation make sense? Does the subsequent derivation of the formula make sense? What can I help with? No questions? Everyone's good? Okay, cool. So then let's try to solve the summation. Okay, so moving right along. We've got 2 times, let's multiply these guys out. So I have, anytime that I have an I in here, I'm going to need to keep it in the summation, but any constants can come out front. So if I multiply these guys, I have n choose I times n, but that n is going to be constant, so it can pop out to the front of the summation. So this first term will be the summation from I equals 0 to n minus 1 over 2, right, of n choose I, and that's it, right, times n, but then I factored that n out to the front because it's constant inside of our summation. People happy with that? Okay, so what can I pull out of my second summation after I multiply the choose in? Multiplying in n choose I, what can I pull out of this term? Yeah, the -2, right? So this will be minus 2 times that same summation, I equals 0 to n minus 1 over 2 of n choose I times I. And that we have to keep inside because the I is changing for each term, right? Everyone see how I did that? Questions? Okay. This one, we're adding up entries in a row of Pascal's triangle. If we added up all the entries in the row, what would we expect to get as a result? 2 to the n. Yeah, excellent. We're not adding all of them up, though. We're only adding up part of it, right? So we do have to be a little bit careful in our analysis of what's going to pop out there, right? Now, in this example, we're going to continue to use n equals 5 as an example. I think that's a big enough n that we can sort of see the pattern, right? It's not quite going to be 2 to the n minus a half. That's not quite right. Let's be really careful, okay? So if we have the sum from I equals 0 to 5 minus 1 over 2. 5 minus 1 over 2 is 2, right? So that is going to be what times n choose I? Or I guess of 5 choose I. What's that going to be? Two to the n minus 1, right? It'll be half of them, right? 1 plus 5 plus 10 is 16. That's half of my total, right? Okay. Well, fine. And what about this guy? What's this guy going to look like? Well, here I'm adding up elements of the triangle, right? Sort of going along the row. But here I'm multiplying by the column number, right? As I go 0, 1, 2, 3, 4, 5, I'm multiplying by those values as I go through, right? So that's kind of interesting. What's going to happen here? Well, what do you think I should do? How do you think I should figure out how to add up rows of Pascal's triangle elements times their column number? Thoughts? Split them. Say more, Nathan. I'm not quite sure what you mean by that. The sum of n. But I can't split them that way because they're not being added, they're being multiplied, right? Yeah, David, I like that idea of just sort of writing out the, oh, I see, writing out the choose notation in terms of factorial. Not exactly. I think we should write out something else though, right? If we're trying to see a pattern with what happens in Pascal's triangle when we multiply the entries by their column number, what could we write out, do you think? The relation between the two. I'm not sure what you mean by that, David. Their difference. Maybe you could hop on the mic. I'm still not quite sure what you're getting at there. Or if anyone else has other ideas of how we could investigate this idea of Pascal's triangle entries times their column number. Okay, so Sean, I could write out the formula, which will have some, that'll have some, maybe that would work actually, right? Let's try it. Let's try to write out the formula. So if I have n choose I times I, what's that going to be? Yeah, maybe we'll end up with I minus 1 factorial in the denominator or something like this, right? So n choose I, that's going to be n factorial divided by n minus I factorial times I factorial, right? And then if I multiply that by I, right, well, that'll just cancel one of the i's off of this factorial here. So it'll come out to n factorial divided by n minus I factorial times I minus 1 factorial. Right? But this doesn't correspond to any sort of choose relation anymore, because I would need a plus 1 in here, or a minus 1 in the parenthesis in order for this to come out to some sort of choose notation, right? So this, I think, is kind of a hot mess, if that makes sense, right? There is this little cancellation here, but I can't really do anything. This formula is gross and I don't like it, right? So what else could we do to sort of see what's happening in the triangle? How do we investigate what's happening in the triangle besides using the formula? What's the dumbest thing you can do? Let me put it that way. So if I have Pascal's triangle here, and let me do it down here. Here I have Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, right? And I want to see what happens if, I multiply each of these numbers by their column value. What could I do? Yeah, multiply them and then write out the whole triangle again. Perfect. And if we do that, something nice is going to happen, okay? Now, this is in column 0. So we always start counting at the left from 0. So this would be in column 0. This is column 0. This is column 1. 0, 1, 2, 0, 1, 2, 3. So I'm just going to multiply through by each of the column numbers and rewrite the triangle. So here goes. This times 0 is 0. Times 0 times 1, this guy, times 0 times 1 times 2, times 0 times 1 times 2 times 3, times 0 times 1 times 2 times 3 times 4, and lastly, times 0 times 1 times 2 times 3 times 4 times 5. What do we get? See the correspondence? Sorry, I kind of squished it so the correspondence isn't as clear as it maybe could have been. 2 times 3 is 6, true. 3 times 4 is 12, good. So what is going on inside of here? What's the contents of this little triangle excluding the zeros? But 12 times 20 is not 30. Maybe English would help. I'm not quite sure what you're getting at with those equations there, guys. You mean that multiplying the number from above to get the number in the middle doesn't quite work? Ah, you're not multiplying. That's not quite it. It's a little bit easier than that. If you forget about the line of zeros for a second, what does this look like? Yeah, it's the same as the original triangle, but you multiply the row by the row number, right? Here's 1, 1, 1, but times 2. 1, 2, 1, but times 3. 1, 3, 3, 1, but times 4. 1, 4, 6, 4, 1 times 5, right? So all you're doing is you're repeating the triangle. You sort of shifted the triangle down diagonally by 1, right? And so what you're actually doing is taking the sum of the previous row numbers and multiplying by that new factor that we've multiplied through, right? Because this thing is going to be 1, 4, 6, 4, 1 plus 4 plus 6 plus 4 plus 1 with the whole thing times 5. And what we're looking for is sums of the rows anyway, right? So what we're going to do is we'll take the previous row, add up all the numbers, and then multiply the result by 5, right? Because if I do 1, 4, 6, 4, 1, right? Add those all up, that's 16. 16 times 5 gives us 80. Well, what do I get here? 10, 40, 80. Same either way. So here I've got 16, the previous row, times 5 is equal to the sum here. People see the pattern? See the correspondence? It's kind of a nifty little trick, right? Yeah. Okay, cool. So then we need to think really carefully about what we're adding if we only go part way through. Okay, because if we added all the way through, it'd be pretty straightforward. We just take 2 to the n minus 1, the sum of the previous row. So n minus 1, previous row, 2 to that, times n. But we're not adding all the way through. We're only adding from 0 up to n minus 1 over 2, right? So what exactly am I adding here? Ideas? Okay, maybe we should do an example. It seems like you guys are a little lost. So in this example, right, where n equals 5, I've got 1 times 5, 5 times 3, and 10 times 1. Or actually, in this case, I'm sorry, this is just the i's. So it'll be 1 times 0, 5 times 1, 10 times 2. So here's my numbers that I'm adding, 1, 5, and 10, right? This is in column 0, this is column 1, and this is column 2, right? So what I'm actually adding here are the 0, 5, and 20, right? The first three items, 0, 1, and 2. So I'm trying to get out a 25 from this thing, right? So how's that going to work? Thoughts? Are you guys lost thinking about it? Anybody? Lost thinking about it? Should I go back a couple steps? How are we doing? You're lost. Okay, a little lost. Okay, great, cool. Let me back up. So what I'm trying to do is I'm trying to find a closed form solution for this summation here. N choose I times I. Now, in order to find this closed form, I drew a new triangle of n choose I times I, right? Where I goes from 0 up to, well, if I did the whole row, it would go from 0 up to n, right? 0, 1, 2, 3, 4, 5, right? And what I did is I multiplied the entries by the triangle, which is 1, 5, 10, 10, 5, 1, multiplied each of those by their column number. So 1 times 0 is 0, 5 times 1 is 5, 10 times 2 is 20, 10 times 3 is 30, 5 times 4 is 20, and 1 times 5 is 5, right? So what I'm doing is I'm multiplying each of these guys by their column number, 0, 1, 2, 3, 4, 5. Okay, and if I multiply all of these guys, these are the numbers that pop out. Are people with me on that part? Does that make sense? And the reason why I'm doing that is because I have n choose I times I. Here's n choose I, this row. Here's times I, which is the little bold numbers on top. Multiply all those, and this is what I get out. Yeah? And Sean, you have a comment. It's the sum of n choose I multiplied by n minus 1. Because okay, so it does have to do with the previous row. And that's what we were talking about a moment ago. Because if you look at this 5, 20, 30, 25, there's another way of interpreting this, which is 5 times all the numbers in the previous row. 5 times 1 is 4. 5 times 4 is 20. 5 times 6 is 30. 5 times 4 is 20 again. 5 times 1 is 5 again, right? So you can go through the previous row, right, and multiply, the previous one, the one above it, times times I, right? Does that make sense? I'm sorry, not times I, times n, pardon me. People happy with that part? That makes sense. Okay. So what can we do then? Well, if we're trying to add up the 0, the 5, and the 20, right? What I could say is that this is going to be equal to the summation of the previous row, but only the first two of them, right? Times n, times 5, right? So what I'm trying to do is I'm trying to find the summation from I equals 0 up to something. Let me write a, here, let me put it down here. Sum from I equals 0 to x of n choose I times I is going to be equal to, this is in row n, right? I don't know how many of them I'm going to add, but that's going to be equal to the previous row, the sum, starting at what? Starting at I equals 0 up to x minus 1 of the previous row, that would be n minus 1 choose I, with that whole thing multiplied by n. What do you guys think? People see what I did? Went up to the previous row. I'm still doing 3 values, these 3 values, which is nothing, right? Times 5 times 1 times 5 times 4 gives me a 20, right? So I'm doing 1 less of them because I'm skipping the 0 at the front. The 0 is not being counted, right? So I'm doing 1 times 5 plus 4 times 5. My 1 is going to be 4 choose 0, right? My 4 is going to come from 4 choose 1. Yeah? You see it now? Makes sense. Okay, so let's see if we can put the whole thing together, right? We've got the first part. The first part's easy. 2 times n times this whole summation we said is 2 to the n minus 1. That's that part we did before, right? Minus 2 times, well, now let's do a little substitution in here. Now we have an n times what? The summation from I equals 0 to whatever we were going to, n minus 1 over 2, quantity minus 1, okay? So that'd be, I guess, n minus 3 over 2 times n minus 1 choose I. What do you guys think? Okay, so we're getting there. We got rid of the I inside of our summation, right? And now I think we can do a little bit better here in terms of reducing this summation here. Now, if we're going back to the previous row, so we've got 1, 4, 6, 4, 1. The previous row is row 4, right? That's so n minus 1. That's going to be what we're choosing. We're doing our i's, right? And how many of them are we doing? Well, we've got 5 minus 3 is 2 over 2 equals 1. So we've got 0 and 1. So we've got 4 choose 0 plus 4 choose 1 times 5. Okay, 4 choose 0 is 1. 4 choose 1 is 4, so that's 5. So this whole summation is 5, n is 5. So that's where I'm getting my 25, which is exactly what I'm trying to find over here, right? Sneaky, right? So let's see if we can resolve this summation. What can we do with this, right? Well, what exactly are we adding, right? We're adding the first 2 items in the prior row times n. Well, the n's fine. We'll just leave that there. But really what I'm trying to resolve is the summation. So I'm trying to add the first 2 things in the previous row, right? Well, you know, if I was to go further down, right? If I was to go down to the row under this, 1, 6, 15, 20, 15, 6, 1, I would be adding the first 3 things in the row. So I'm skipping the middle element, right? I'm only adding the 1 and the 4. I'm not doing the central one. If I was trying to do, you know, if I was trying to find 7 and looking through row 6, I would do 1, 6, 15, but I wouldn't do the 20. The center one is left out, right? So can someone see a formula for how to find this thing? To go in an odd numbered row and add up everything up until but not including the central term? what would a summation like that look like, right? And let me get you started. What if we add up everything in the row? What are we going to get? If I add up everything in the n minus first row, what's going to pop out? The whole row sum. Two to the n minus 1, right? So if I added up everything in the row, it would be 2 to the n minus 1. Let me make a little note over here. It'd be 2 to the n minus 1. Okay. What if I only wanted half of the row? Then what would I have? Divided by 2. And what if I wanted to exclude the central term? What would that be? Not quite, David. That's not quite it. What's the name of the central term here? What choose what would be this guy. N choose n over 2, right? Because it's, well, close. From the previous row, I think we need some minus 1s on there. But you have the idea, right? It's n choose halfway across, right? So if I wanted only the 1 and the 4, I would have the grand total, which is 2 to the n minus 1, minus the central term, which would be n minus 1 choose n minus 1 over 2. That whole thing divided by 2. Right? Is everyone happy with that? Questions? So you take the whole thing, get rid of the central term, and whatever you have left, divide in half. Right? So let's see if we can put it all together. So now what we've got is we've got 2 times n times 2 to the n minus 1. So that's just n 2 to the n minus 4 times n. There's a 2 to the n minus 1 divided by 2, right? So this first term here, I have 2 to the n minus 1 times a 2 here, and then these 2's cancel. So this is going to be minus n 2 to the n for this part of it right here, right? Because I have 2 times n times this guy. There we go. This guy equals this whole thing, right? And if I just take the first half of it, I have 2 times 2 is a 4, and so the 2 cancels one of those. I'm left with a minus 2 times 2 to the n minus 1, so that gives me a minus 2 to the n. And what am I left with? I'm left with minus a minus, so that's a plus. These 2's cancel again, right? And then inside of here, I've got a, what? 2n n minus 1 choose n minus 1 over 2. These guys cancel, and here's my final formula. this can actually be helped a little bit, I think. Here I have an n minus 1 and n minus 1 divided by 2, but I'm multiplying by 2n, right? So maybe I can simplify this a little bit. So what have I got here? So here I've got 2n times n factorial divided by, oops, sorry, screwed it up already, n minus 1 factorial divided by what? N minus 1 minus n minus 1 over 2 quantity factorial times n minus 1 over 2 factorial. See, can I do anything with that? Maybe this is a bad way of doing it. Let me do it a different way. I'm thinking about something in the middle of the triangle. N minus 1, choose n minus 1 over 2, right? And I'm multiplying that by 2. Okay, so what if I take something in the middle of the triangle, right? Like this 3 is in the middle, or the 6 is in the middle, or the 10 is in the middle, right? So I take something that's in the middle, like this 3, and multiply by 2. What do I get? 3 times 2 gives me what? Six, which is the one in the center of the next row. If I had my next row down here, 1, 6, 15, 20, 15, 6, 1, I take this 10 and multiply by 2, what do I get? Well, the central one on the next row. So I can actually get rid of this 2 and move from the minus 1s and just get rid of them, right? Because anytime I have something like 3 and I want to move down back to from n minus 1 to n down to the next row, multiplying by 2 just pops me right there to that central number. So what this is really equal to is n times n choose n over 2. See that? This used a bunch of different ways of manipulating the triangle and finding patterns inside of it, which is, sort of the whole game, right? How do we go from even to odd? Good question. Let me address that in just a moment, right? So before we get there, let's check this, right? Here's our final answer, but let's see if it even makes any sense. So this is to find my total, right? To find the expected value, I would divide by 2 to the n. But just to find the total, let's see if it works. If I have 5, maybe I should do, well, let's see. I did this for an odd number. Let's see if it works for evens, right? So for 4 here, I would have, and here's my formula, remember, n times n choose n over 2 is supposed to give me my total, right? So let's see if that works. Okay, 3, let's do some even ones, right? 4 times 4 choose 2. So what's 4 choose 2? 6, right? 4 times 6 is 24. That one worked. Okay, let's try another one. 6 times 6 choose 3. What's 6 choose 3? 6 choose 3, anybody? Close, not 40, but you're almost there. 20, right? 6 choose 3 is 20. 20 times 6, 120. How about an easier one? Let's do 2, right? 2 choose 1 is 2. 2 times 2 is 4, right? So anytime I have an even number, I have an even row, I can pop it in for n, and I'm getting out the right total. If you want the EV, well, then you just divide by 2 to the n, and that gives you the expected value, right? So for the expected value, here's my whole formula, right? Let me pause there. Who's got questions? How can I help? No questions, huh? Okay. Okay. Cool. I was working on it before class. Okay. That one I had to go through before class because that's real nasty. And the next part, I didn't have time to get through, so we're going to do it live, and we'll see how badly I screw it up. So here goes. So what I want to investigate next is this. N choose n over 2. Okay. Now, if I was to use a formula on this guy, right, what would it look like? Well, it would be n factorial divided by the top minus the bottom factorial, which would be what? What's the top minus the bottom? N over 2. So I'd have an n over 2 factorial, right, times the bottom one factorial, which is just another n over 2 factorial. So I could combine these. I could have, 2 times n over 2 factorial, I guess. But that doesn't really get me that far, right? I'd like a closed form, and factorial is not closed form, right? Factorial is a recursive formula, right? It says n times n minus 1 times n minus 2, etc., right? So if I wanted a closed form for this guy, right, I don't think this is the sort of the direction I would want to go to find it, okay? So let me tell you something surprising, okay? Which is that n choose n over 2 is approximately equal to 4 to the n divided by the square root of pi times n. Now that should make you unhappy, right? Is everyone unhappy? At this point, you're too lost to care. David's unhappy. Okay, good, right? So how the heck could this be possible? I mean, that's just wild, right? How do we get a square root and a pi in here when we're talking about choose notation? I mean, maybe the 4 to the n makes sense. Maybe we were talking about 2 to the n's earlier. Okay, fine, right? But a square root and a pi, like, how the heck is that possible, right? So what do you guys think? Should we go through it? What would happen if we did go through it? Let me give you our goal, okay? Our pay. I'll give you the payoff first to give you a little motivation, right? Because what I wanted is I wanted n times this thing, my EV, right, is going to be n times n choose n over 2 divided by 2 to the n, right? Now, if I can substitute this guy into here, right, what's my result going to be? Well, then my EV is going to be n times 4 to the n divided by root pi n times 2 to the n, right? Is everyone happy with that? Yeah, okay. So, oh, and pardon me, I screwed that up a little bit, sorry. Pardon me for a moment. I broke it. Back up just a step. 2n choose n is this guy, okay? So what's n choose n over 2 gonna be? Well, I just substitute in n over 2 into my formula, right? So in that case, I'm gonna have n over 2 up here, right? 4 to the n over 2 divided by root pi n over 2, right? Sorry, I screwed that up. That's for 2 to the n and n rather than n and n and a half n, right? In which case, on top here, this isn't going to be a 4 to the n. What's 4 to the n over 2 going to be? How do those exponents play out? So if I have 4 to half of an exponent, right? How do those work out? It's just 2 to the n, right? So this guy's just going to be 2 to the n, right? Which is nice because these guys will cancel, right? And then on the bottom, I just have a little n over 2 factor here, right? So now my EV equals n over root pi n over 2. And now what do I do? Can I simplify this any further? Square it? Well, why would I square it? Never mind. Okay, I can square something. You're on the right track. What is it that I want to square? What do I square in here to simplify the root? Not the square root, actually. Okay, I could find the whole expected value squared. That's not quite what I'm looking for. Let me show you what I mean. I can square the n and put it under the root, right? So what I could do is this. I could do that, right? Is everyone happy with that? And then the n's will cancel, right? Does everyone see what I did? Square the n and then just include it in the root. So now the n's will cancel, right? The 2 is a division in the numerator, so that moves up to the denominator. So the whole thing is the square root of 2n over pi. And of course, this is approximate, right? So I should say approximately equal to. Which is a really nice, clean little formula, right? Like I'm real pleased that after that insanity, this is what pops out. That makes me happy, right? Does that make everyone else happy? Yes, okay. So now what remains to show is this guy. Why is it that 2 times n choose n is approximately this thing with a root and the pi and all this insanity, right? The approximation gets better for larger n. Yeah, so the approximation becomes better as n gets larger, right? And if we want to think about the expected value of the number of steps, right, which is the whole idea here, we're wondering about our random walk where we're sort of wandering around from the origin, right? I think that gets to be interesting when you take, 100 steps or 1,000 steps or 1,000,000 steps. If you take 5 steps away from the origin, why are you even concerned what the expected value is? I mean, sort of the whole idea here is to think about what's happening to your distance from the origin as n increases. And here's a nice little function that gives you an approximation of that, right? Are people follow? Does that kind of make sense? I'm sort of wondering about the asymptotic behavior rather than about, specific precise results for small n, right? I was just using specific results for small n to build up our understanding of the formula, right? But really in the long term, what I'm curious about with expected value is, well, how does it behave if I walk a long way, right? If I walk back and forth randomly along a line for a long time, after a while, how long, how far am I going to be from the origin after a long time? And apparently it says, well, it's going to be on the order of the square root of the number of steps I've taken, right? Yeah. So David, you have a nice idea there. The number of steps is mapped like a sinusoidal function. So we're not going to think about the number of steps as a sine wave exactly, but what we are going to do is use a sine function to investigate what this guy is equal to, okay? But unfortunately, we're running out of time. So I think what I'd like to do, oh, and we didn't even talk about lab. Oof, oh, I forgot. Uh-oh. Wait, are we almost out of time? We go to 3, 4, yeah, we're almost out of time. So I think what I want to do in the remaining 5 minutes is I'm going to go 5 minutes over. Let's talk about the lab, and we'll talk a little bit more about this on Monday if we have some extra time. But I'll leave this sort of as a mystery for now. It's called an Euler product. If anyone wants to look it up online, right? If someone wants to investigate why this is, there's a fun little trick you can do with the sine function to show that this thing is true. But let's talk about the lab for a moment, because I totally forgot about it. Sorry. Let's jump into that. Okay, so for the lab this week, what I want you guys to do is make a picture of a random walk. Now, this random walk is going to be in 3 dimensions rather than in 1 dimension. But you're not going to be, analyzing the equations for it or anything like that. You're just going to be looking at one. You're going to be drawing one, I should say. You're going to be drawing a 3-dimensional random walk. Let me download this guy. Pull up this. Pop this up here. This guy. Participants back. Okay, good. All right, so the basic idea of what we're going to do is it's going to be another one of these 3D block worlds, okay? But this time in our 3D block world, what we're going to do is we're going to start off at the origin and we're going to randomly move around in space, okay? So by that I mean we're going to be equally likely to move up or down or left or right or back or forth, back or front, right? And if we continue to do that random walk and leave a record of each cube that we got to, then we'll come out with a kind of a cute little picture which shows the way that we walked around, okay? So here's the idea. I've got my init array. Need to go through that. Draw object here. This is going to be the same as before. I just have this array of cubes, and whenever the array contents is true, I draw a cube there. So really what I'm going to do is just initialize my array and then draw it. Here's the code to draw a cube, the main function, display. I don't think there's anything else in here. Yep, all that is the same as it used to be. Okay, so all that I'm really doing is going through my 3D array with my triply nested for loops. If the array is true at that point, I'll draw a cube there. So the only thing that you really need to look at is this function, the init array function, right? Which starts in the middle of the drawing area with an integer r, and I'm going to be using random numbers because it's a random walk. Okay. Now here's what I'm going to do. I'm going to go up to a res squared number of steps, and each time I'm going to randomly choose if I'm going to go in the I direction or the J direction or the K direction, right? I is back and forth, J is up and down, K is left and right. Or sorry, I is left and right, J is up and down, K is back and forth. And how am I going to do that? Well, let's take I as an example, right? I take my current I value and I add on 2 times a random number mod 2 minus 1. What is this doing to my value for I? So what's this line of code doing to I, do you think? Okay, it's equal to 0 or 1. Okay, so this guy is equal to 0 or 1 because any number mod 2 is going to be equal to 0 or 1. I multiply that by 2, so now I either get 2 times 0 or 2 times 1. So I get out either a 0 or a 2 from this guy. 0 or a 2 minus 1 is either negative 1 or 1. So I'm going to add to I either negative 1 or 1, and then look and make sure I'm not at the border, right? If I end up going past the resolution, past the border, I reset I to be just to the side of it. Or if I go less than the border, my I goes negative, then I just set it back to 0. So these two if statements are just to ensure that I don't walk outside my cube, or I guess fly, because it's in 3 dimensions. It's a random flight, right? So in my random flight, make sure that I don't fly outside the cube. Same thing's going on here in case 1, just a little bit different way of looking at it, right? Where here I'm saying, hey, I take a random number, mod by 100. If it works, right? If I get it works if I get a number that's 50 or larger, right? Otherwise, and then I'll go upward. Otherwise, I'll go downward, right? And same thing, make sure I don't fly outside the box. And then K is working the same way that I did, right? Now J is a little different because it's a little skewed, right? Here I'm a little bit more likely to go upward than downward, right? Because my random number is from 50 to 99. There's one more of those than there is one of these. So I'm slightly more likely to go upward than downward. Let me show you what it does. It's going to be a block trail of our random flight. There it is, right? So I started in the middle, which is this guy, and then flew all around. And if I zoom in a little bit here, right, you can see all of these blocks were the trail of where my random flight took me. Yeah. So what you could do, what I'd like you to do is to change the parameters of the likelihood of going left or right, the likelihood of going up or down, the likelihood of going back or front. And that'll give you a little bit different kind of picture that pops out with your cubes as a result of that. So this guy in here, right? I'm slightly more likely to go up than down. What if I change this to be, 40 instead of 49? So I'm much more likely to go up than down. So watch what happens. See? Much more likely to go up. And you can see that the whole thing is sort of just sitting right on the top of the cube, right? I'm just as likely to go back or forth, just as likely to go left or right, but much more likely to go up than down. You can see my random walk has taken me to a point where I'm basically just bouncing off the top of the cube the whole time, right? And if you change the likelihood of which ways you're going to move, you can make it make different kinds of shapes with your random walk. What do you guys think? Does that make sense? Or random flight, I should say. Any questions? You see what you're supposed to do? Makes sense. Excellent. Okay, so I'm sorry I didn't get to the Euler product. If we have a little bit of time next Monday, I'll see if I can trot that out. But otherwise, good luck on your proofs in your lab this week, and I will see you Monday. Have a good one, guys.